All right, welcome back from lunch. Our next speaker is Sunny, who will tell us all about how to build a computer with QLDPC codes. Please take it away.
Thanks, Nico. Hi, everyone. My name is Sunny. I'm a grad student from MIT. Today, I want to tell you about building a quantum computer with QLDPC codes. This has been a very popular topic in the field of QEC over the past 5 years or so, and we as a community have made a lot of progress. That progress has changed the timeline for practical FTQC. And what used to be a very far away goal, namely having quantum computers that runs logical qubits or runs logical circuits on logical qubits, now seems to be within reach in maybe the next few years, if we believe at least in company timelines. So for those of us who may not think about QEC on a very regular basis, that may be quite surprising or even a little hard to believe. So the purpose of my talk today is to give you an overview of where we are in terms of building a computer with LDPC codes, what led us here, and where we should go, in my opinion. So let me start with where we are in terms of FTQC, and I think the best way to start is to look at the transition from the NISQ era, noisy intermediate scale quantum devices, to the early FTQC era that we'll see pretty soon. So back in 2018, in a very famous paper, Quantum Computing in the NISQ Era and Beyond, Professor John Preskill wrote the following, which is, the era of FTQC, fault-tolerant quantum computing, looks pretty far away. It's not clear how or when we're going to get there. And for that reason, he argued, we should look at these near-term devices, which are noisy intermediate scale NISQ devices, and see what we can do with them. But now in 2026, if we look around and look at industry timelines, they have all converged to fault tolerance. The companies are aiming to deliver hundreds to thousands of logical qubits, from megaquote to teraquote operations, which means 10 to the 6 to 10 to the 12 quantum operations, before around 2030. Now, obviously, industry timelines change a lot, but besides industry, the same trend can be seen in academia. So here's a plot that looks at archive postings in the past 10 years, in the quantum physics category, and I filtered out some keywords in the abstract. So the thing to see here is that around 2018, after the NISQ paper, the keyword NISQ obviously showed up quite a lot and growth substantially. What's also interesting to see is around 2021, the keywords fault-tolerant, error correction, and QLDPC codes have seen gradual increase, and now they're taking up fault tolerance about 5% of all the postings now. And it's more than NISQ. The keyword NISQ have mostly plateaued or even reduced in relative frequency. And I think this kind of is quite reflective of the shift that we're going through right now, which is we went from, maybe we'll get large-scale FTQC in 20 to 30 years, depending on how things go, to there's a slight chance that we might break crypto before 2030. This is a pretty significant change. Unless you're very up-to-date on QEC, this could be very surprising. So what happened? Well, I think the best answer I can give about what happened is that there is the developments in experiments over the last few years and the developments in QEC theory has really converged and produced a lot of amazing results. So let me just look at some important developments that I can recall. This is in no way a comprehensive list. It's just what's showing up on my attention. In terms of QEC theory, around 2019, we get these new theories for LDPC codes, which have led to the asymptotically good codes in 2021. Also around 2019, we're seeing these new decoding algorithms or more study on LDPC decoding, primarily with belief propagation, but more recently with machine learning. Around 2020, we see these developments of simulation software, notably STIM, and a lot of these open source decoders. And I think this software development is very important because they enabled simulations and benchmarking of finite scale FTQC protocols, which were pretty difficult to do before these tools become widely available. Around 2023, there's now a lot of focus on constructing and developing finite size LDPC codes and studying their implementation on hardware. Also around 2023, there's a lot of study on computational methods for LDPC codes, notably on LDPC surgery and high-rate transversal logic, both of which I'll discuss a little more later. Now on experiments, I'm not an experimentalist. I'm just recalling what things from my mind. But around 2022, we see a lot of developments with reconfigurable qubits that enable non-local connectivity, which is needed for LDPC codes. 2023, we see subthreshold surface code memory. That was debatable back then, but since then there has been more improvements to the experiment, and we do see that larger codes give more error suppression. Also, 2023, we see long-range connections that support modular architectures, which is important for basically all sorts of most of the hardware platforms. 2024, we see demonstration of magic state distillation and cultivation and later gate teleportation, consumption of magic states. And consistently, we're seeing lower gate error rate, larger systems, and better physical control of our qubits. So if we add all of these up, I listed a lot of things, but if we add all of these up, on the side of QEC Siri, we see a lot of finite scale proposals to reduce space overhead with LDPC code, because space overhead has been one of the crucial bottlenecks. And in experiments, we see a lot of new hardware capabilities, lower physical and logical error rates, and simply larger scale systems. Now, the result of these two sides converging is that we now see a lot of new proposals for finite size FTQC in the year 2026 and also 2025. I want to discuss some of them. So the first one is the estimation done by Craig Gidney on factoring back in 2025. This is a surface code architecture. The computation is done with a technique called lattice surgery. It uses a lot of new QEC developments, including cultivation and code concatenation. And the titular claim is that RSA 2048 can be done in less than 1 million qubits, less than a week on superconducting qubits. So it's been a year since this estimate, and I think a lot of us look at it as like the new baseline to look at resource estimation for factoring. Around the same time, there was IBM's Bicycle architecture, which is a very different design. This is a modular LDPC architecture where the computation is done by LDPC surgery. If you don't know what that is, I'll go into it in a little bit later. The main takeaway from this architecture is that it's about 10 times less qubits than surface code architecture, so more space efficient, but it takes about 10 times slower than surface code, which means there's a space-time trade-off. It looks very interesting, and I'll get into this space-time trade-off a little later. Now, more recently, a startup company called Iceberg announced that they intend to break RSA 2048 with 100,000 qubits on a neutral atom device. But to implement this factoring algorithm, it would take 30,000 days with standard assumptions. That's a lot of days. Shortly after that, the startup company Oratomic announced an even more surprising result, which is they estimated that breaking ECC 256 can be done with 10,000 qubits in 1,000 days on neutral atom computer. RSA 2048 can be done with 11,000 qubit and 43,000 days, okay? Also on neutral atom computer. Now, in a few months after that, more proposals have been published, including from IMQ, from an academic collaboration among Duke, UT Austin, and Yale, from Quera, from Google, and many more that I don't have space to include here. So the amount of fault-tolerant architecture proposals have really increased in the past 2 years. And this is the result of, as we discussed, convergence of experiments in theory. Yes?
Parallelize these and cut the runtime by maybe a factor of 10 or so?
Yes, if you...
So you could, since it's just independent runs, you could actually get a reduction by a factor of 10 in the runtime there. So this very long runtime of 43,000 days could be cut quite substantially.
Yeah, there's a lot of trade-off there. If you run things in parallel, then potentially you want to build like multiple copies of the same computer.
You build 10 computers instead of just one.
Yeah, there's a lot of parallelism trade-off there, and I will get into the time overhead a little bit later in the talk. Yeah. Thanks for the comment. Great. So before going into the details of this proposal, I want to emphasize that while many of these works are very solid, these are still proposals and estimates. They are not finalized reports. Okay? In fact, some of the assumptions and methods used in some of these works are under active discussion in the community. So when you look at these papers, you should not see them and be like, they've solved all of their problems. It's actually on the contrary. There are lots of things that needs to be figured out, and these numbers may move a lot as we get them to be more and more precise. So lots of things to be figured out and a lot of critical work to be done. We should not look at these resource estimates and think that they reflect like accurately what's going to get done or what's going to get built. But with that being said, I think it's very clear that these works are kind of pointing in a similar direction, and I want to highlight that direction. So the first observation is that all of the architectures besides Craig Guinea's architecture are done by LDPC codes. And we see dramatic reduction in the space overhead of computation, which has been a crucial bottleneck for near-term FTQC. The second observation is that about half of these proposals use LDPC surgery as the computational backbone for their architecture. So I'll go into what surgery is later in the talk. The third observation is that there's a significant increase in time overhead to the point of infeasible. And a very good question to ask is whether this time overhead is fundamental, whether by using more efficient space, more space-efficient codes would necessarily incur a time trade-off. And the answer I want to convince you of today is no, at least not yet, not showing up in these numbers yet. I'll explain that. So this is where we are now. And for the rest of this talk, I want to tell you about how we got here, the key techniques, and what are ways to improve from the existing architectures. So for the first part, I'll give you an overview of modern LDPC architectures, its components, on a very high level, what are the things that it's built from. And for the next part, I will tell you about this method called LDPC surgery, which is a key technique that enabled half of these new architectures. And in the process, I'll talk about the time overhead. And finally, I will end with some outlook on the days of early FTQC. Great. So on to LDPC architectures. Let me start by a very high-level sketch of what they look like. So there are a few components. The first component is a memory. This is the storage unit for especially those idling qubits in your logical circuit, right? In many of our applications, a logical circuit, a lot of the qubits are idling while only a small part of the qubits are actively being computed on. So this is kind of the overall storage units for all of your logical qubits. Sometimes we call it code storage. There's obviously the compute zones, which is for all the active qubits that's experiencing computation right now. And there's the third component, which is a resource state factory, typically magic state factories. The usual way we think about computation happening is that we're loading the logical qubits from the memory to the compute zone, and the compute zone is going to ask for these resource states, usually magic states, from the factories. And at the compute zone, we will implement a lot of non-Clifford unitaries or computations to act on the active qubits. This is a very high-level sketch. Let me go into a little more detail on what each of these components look like. So let's start with memory. A lot of these memories are done with LDPC codes. I guess this is a good time to explain that LDPC stands for low density parity check. These are codes that have high encoding rates but have higher connectivity requirements than surface codes. So when I say higher connectivity requirement, I really mean it's harder to build in hardware. So there are some notable examples of LDPC codes. There's the bivariate bicycle code, which have parameters 144, 12, 12. So how do you read these numbers if you're not familiar with the notation before? This is saying using 144 physical qubits, we're encoding 12 logical qubits with distance 12. Okay, so the typical number we care is the distance. We want it to be high. The rate, which is 12 over 144 here. Now, there are other examples. There's the lifted balance product codes, which are very popular. And very recently, there are these codes called affine permutation matrices codes that are just developed over the past few months. And the thing to note here is that 580 is more than half of 1152, which means we have encoding rate of more than, or slightly more than half. This is really, really surprising, especially when we compare it to surface codes. You can see that the space overhead of encoding can be reduced by a factor of more than 100, especially at slightly larger scales. Question?
The last slide. Is there any fundamental reason why you have to have a separate processor than a memory? Or like,
Is there a fundamental reason why there's a compute zone other than a memory zone?
Yeah, or like why you should have a compute zone and a memory zone as opposed to just in place everything.
There's no fundamental reason. You can't do things in place. Actually, I will discuss methods of how to do things in place. So it's just a conceptual picture. Other questions? Great. So yeah, this is QLDPC codes, and there are a couple common memory designs that we use nowadays. You can use few big blocks. You can use many small blocks, Or you can use concatenated codes, especially demonstrated by some of the recent works. I won't go into the details of these designs, but I will say that there's a trade-off among modularity, space efficiency, and access speed among all of these memory designs. So the next component is resource state factory. And basically all FTQC proposals, especially modern ones, uses some form of resource state, most notably magic states for T states and for T gates and for CCZ gates. And this recent architecture mostly uses two primitives, the first one being magic state cultivation. So this is a primitive where we prepare a good magic state, good meaning the fidelity is around 10 to the minus 5 to 10 to the minus 9, at low distance, and we rapidly escape into a large distance surface code. So this is a rough schematic of it. The second primitive is something that's been around for a lot longer. This is magic state distillation. On a high level, we take many magic states at large distance and distill them into fewer magic states of better quality. So typically, you should think that we have something that start at 10 to the minus 6 in fidelity and get to 10 to the minus 12 in fidelity, which is enough for a lot of our applications. That's magic state distillation. In these modern architectures, the typical factory will cultivate first in surface code to a sufficient distance. We'll load them into an LDPC code, which is a lot more compact, and we'll distill. So in this way, you get the benefit of having good magic states to begin with, and you also get the benefit of space overhead on LDPC code. And I would say that magic state production is one of the key bottlenecks in current architectures. I'll talk more on that later. But that's what resource factories look like. Now onto the compute zone, and this is, there are two main ways to compute on LDPC codes that we understand now. One is using low depth unitaries, and the other is using Pauli measurements. So let me discuss both of those a little bit, because there's been a lot of work on LDPC computation. It's honestly a little hard to follow as someone who works on LDPC computation. So let me discuss that in a little more detail. In terms of low-depth unitaries, the typical example is a transversal CNOT, or sometimes we call low-depth unitaries transversal gates as well. But a typical example is a transversal CNOT between two copies of the same code. The idea is simply we use a constant depth physical circuit to implement a logical unitary. And it has its advantage and disadvantage. The main advantage is that these gates are usually very parallel, they're very fast, and they have no space overhead. The disadvantage is that the logical control that you get by using low depth unitary is often constrained and limited depending on your code. The other thing is that it usually requires you to move your qubits around to reconfigure your qubits so that you can implement things transversally. On the other hand, we have Pauli measurements. This is a very different primitive. It is usually implemented by code surgery, such as lattice surgery. Sometimes we implement it with cat states. And the high-level idea is we'll implement computation by extracting Pauli observables from the logical qubits. Okay? I'll explain what this means later. But the main advantage with Pauli measurement is that it gives you very complex, almost complete logical control over your qubits, and it can work with fixed connectivity. You don't need to move things around. However, the disadvantage is that this is usually slower. The logical control is often sequential in a lot of the cases we're looking at. So this is, in my opinion, a pretty clear comparison of the two main primitives we have. Yes?
When you say logical control, does that mean like the addressability of the qubits within the block, or also like which specific gates?
Both of that, and that's a very good question. So what do I mean by logical control? For instance, in an LDPC code, you have like maybe 50 logical qubits encoded in like 500 qubits. Then the question of logical control is, in general, I just want to implement some set of gates on these 50 logical qubits. There's no guarantee that they're going to be the same gate. There's no guarantee that they're all going to be Cliffords or whatsoever. So the question is, how can I best implement that? For instance, with transversal gates, what happens is it's very good at implementing the same gate on all the logical qubits. While with surgery, you can implement very complicated gates, but often one at a time. So that's what I mean by logical control. Thanks for the question. Great. So these are the two primitives. And why have a lot of these modern architectures choose to use surgery at this moment? So LDPC surgery, or surgery on LDPC code, is a new technique that has advanced quite rapidly over the past few years. It has a few desirable properties that make it very nice for near-term application. So the first thing is that it's provably fault-tolerant and low overhead. It gives you complete or complex logical control, even though it's often sequential. It is effective starting at very small scale. So with as few as 400 physical qubits, we can control 11 logical qubits at distance 12. This is something that were quite surprising before we found out. And furthermore, LDPC surgery can be implemented on different qubit platforms. It can be done in superconducting, obviously on neutral atoms, also on photons. A lot of these hardware platforms can support LDPC surgery. But with all of that being said, I think the key method that we're using surgery right now to do these resource estimation is that surgery and low-depth unitaries are very similar to classical CPUs and classical GPUs. The first one gives you sequential and complex logical control, while the second one gives you parallel and structured logical control. Okay? And in the days of early FTQC, when you want to implement specific tasks as early as soon as possible, surgery becomes a very natural choice. So let me take this analogy one step further. If FTQC is like printing, printing a document, then you have two types of printing presses here. One that prints 5 words at a time, any words of your choice. The other one prints 100 copies of the same word at a time. Now, when resource is limited and you really, really want to print one specific essay, you use the first press. And this is sequential surgery, which was studied and adopted in recent architectures. Now, when you want to print many copies of the same essay, for instance, if your execution is very, very parallel and it's it's the same subroutine that's being implemented in parallel, then you want to use the second press. And this is batched parallel computation with transversal gates. So this is the analogy that I want to describe. And I want to say that surgery can give parallel structured logical control as well, but that's something that's very recent developments that we're just starting to understand. So, yeah. Okay. This is what I want to say about LDPC architecture on a very high level. For the next part of this talk, I want to tell you more about surgery and give you a very simple conceptual model to think about these surgery architectures so that you can understand and reason about them without much without spending too much time in QEC. Great. So let me start by what I mean. So let me start by explaining Pauli measurements. What does it mean? Usually we think of a Clifford plus T circuit. It is universal FTQC. You can take my words that such a Clifford plus T circuit can be compiled into 2 primitives. I won't go into the details. But the 2 primitives are 1, measurements of Pauli observables. Sometimes we call them PPM, standing for Pauli product measurements. And 2, magic state production. Okay? And this model of computation is called Pauli-based computation. Here's a circuit diagram showing you how that compilation goes. You can stare at it if you want, but you can also just take my words for it. Now, code surgery is a way to measure logical Pauli observables fault tolerantly. It turns out that when you encode your logical qubits and you want to extract the logical Pauli observables, it's pretty hard generically. And surgery is offering you a way to do it fault tolerantly. The high-level idea is the following. So we'll start with a quantum code, which is nothing more than a stabilizer group. We'll measure a new stabilizer group, which is different from the group we started with. And in this new stabilizer group, the large logical Pauli operator that you want to measure will be decomposed into a product of small Pauli stabilizers. Okay? I think this is the key idea of surgery, and this weight reduction effect from large operator to small operator is what gives you fault tolerance. So let me show a very quick example on lattice surgery. I promise I won't go into all the details, but imagine you have 2 patches of surface code, each having 1 logical qubit, and you want to measure the x tensor x Pauli observable between the 2 surface codes. So the way you do it is we'll introduce some new stabilizers in the middle of these 2 surface codes and measure these new stabilizers for enough number of rounds. And the weight reduction effect is here. You take the product of the new stabilizers you've introduced, it gives you the logical operator you're trying to measure. Okay? So by simply measuring these new stabilizers for enough rounds, you get the logical Pauli observable. And once you're done, you go back to your 2 separate stabilizer group of surface codes, and then you continue with your computation, and you go from there. Very high-level description of surgery. Now, we can try to do this with LDPC codes, but the one thing about LDPC codes that we have talked about briefly is that logical control on high-rate codes, meaning that you have a linear number of logical qubits per physical qubit, is really fundamentally different from logical control on these constant dimension codes. Okay? Because you simply have a lot more qubits that you want to control inside the same block. A very good way to see this is to count the number of Pauli observables you have. When you have one logical qubit, there are like 3 non-trivial Pauli observables. And when you have k logical qubits, you have 4 to the k, well, 4 to the k minus 1 of those PPMs that you potentially want to implement. This blows up very quickly. And the conceptual way that I sometimes think about this is you have a quantum LDPC code, and your logical operators are like these different irregular shapes on the LDPC code that they overlap all over the place, and they're very, very dense. And that's a logical control problem we have. So the current model of sequential surgery that has been developed over the past few years is the following. For any code, given any set of logical Pauli observables, think of this as the amount of logical control you want on your logical qubits. We can build an extractor system that gives you that logical control. You can measure any operator from the set of logical Paulis you've chosen. But the logical control is sequential, one at a time. I want to pause here for a moment to see if there are questions, because that's a very non-trivial sentence. Yes?
And is this provably fault tolerant?
Yes, provably fault tolerant.
What is the intuition for why it's provably fault tolerant?
Why it's provably fault tolerant? Right. So you will repeat I will show on the next slide what operationally we do when we do a measurement, but you will repeat the measurement for O of D rounds. So it's very similar to like why LDPC memory is fault tolerant when you give it enough rounds. Other questions? Great. So this is the model of sequential surgery. I want to say that these extractors, they are provably fault tolerant. The size is pretty reasonable. Usually I think of it as roughly the same size as memory. But the key idea to take away really is that these extractors, they turn the LDPC memories, which were previously just storing the logical information, into processors that give you control over the logical qubits. Now, with that in mind, this model of sequential surgery gives us a pretty clean way to understand the computation in these recent architectures. And we can understand them by looking at the extractor gadgets they have and the number of operators they cover. Okay? So on one end, we have these single operator extractors, which means they can measure 1, sometimes 2 operators, depending on your choice. And some of the works here are actually early works on LDPC surgery that have inspired a lot of later works. Now, you also have these extractor gadgets that are a little bigger. It can measure around 8 to 16 operators. These are the extractors used by IBM in the bicycle architecture. And if you combine it with some low-depth unitaries or automorphism gates, you can reach about hundreds of operators. We also have these slightly bigger extractors from the Iceberg paper. And they, again, measure around 16 operators. But because they're on reconfigurable qubits, they can move the physical qubits around. And by doing that, they can access all 4 to the k operators. And finally, there are these full extractors, which simply just is a single system that can measure any operator of your choice, doesn't require reconfigurable qubits. So this is one way to look at the logical control we have in these recent architectures. Now, just to be thorough on the operational meaning of all of this, when I say it gives you logical control, what does it really mean on an LDPC code? So on a very high level, I start with a code and an operator that I want to measure. It's a Pauli operator, let's say. I will initialize the ancilla qubits in the extractor system in a specific product state, and I'll define a new set of stabilizers supported on the code and the ancilla qubits. This new set of stabilizers, I'll measure them for enough number of rounds. The logical operator I want to measure will be a product of new stabilizers, all the same intuition from lattice surgery. And once I'm done, I'll measure out the ancilla qubits, return back to the code, and continue with my computation. So this is operationally what LDPC surgery is. Yes?
If I just have a surface code, what is it? Let's just say I want to measure a single logical qubit in a surface code.
Yeah.
what would the extractor be?
It would just be a single strip of extra stabilizers. So usually in lattice surgery, you have two patches and you add a strip of stabilizers in the middle. If now you just have one surface coat, you just have that strip of stabilizers.
So a strip on the side, nothing else, or a strip?
Exactly, with nothing else. Yes?
When you say a single strip, what do you mean? Like you're saying you take your surface coat and then you bring in no, you have a single surface coat and I want to measure, let's say, just a single Z.
Yeah.
What were you saying?
So if you have a single surface coat and you want to measure a single Z, one way to do it is just destructive measurement. But if you want to do it with surgery, you introduce the ancillous qubits and stabilizers kind of in the middle, this strip in the middle, which was previously between two surface coats, but now you only have one. And that will also give you a measurement of the single logical operator in the surface coat.
If your ancillary system is small, is that fault tolerant?
Surface code is slightly different because you only have like one logical qubit, which is why I think that's fault tolerant. But on an LDPC code, it's not just going to be a single strip. Okay. Thanks for the questions. Okay. Great, so that's the operational meaning. But now that we understand the logical control that an extractor gives you, putting together an architecture is really, really easy. It's almost just like putting together Lego pieces. So let me show you how I put together my Lego pieces. So the first step is you choose your LDPC codes in your memory. So maybe you choose a bunch of blocks, whichever you prefer. The second step is you choose the logical control you want on these logical qubits, which is choosing your extractors. So build these processing units on top of the memory. You can do this in block. There are many design choices whether you want to do it on the memory directly or on a separate processor. And this choice of logical control has a very deep impact on the compilation methods that we'll use and the resource budget that we'll have for specific applications. The third step is you choose your magic state factories. Again, there are a lot of designs. You can pick whichever you want. And finally, we'll just connect them up with adapters. This is just one way to make sure that the logical information can flow from disjoint blocks. Okay? And this is an LDPC architecture. Great. So with that in mind, let's look at some of the design choices that were made in these recent architectures. There's one which includes IBM's bicycle architecture and Iceberg's and Oratomics architecture. So there's one similarity, which is they implement sequential logic in the following sense. Every CCZ gate or T gate in the circuit is compiled into one, usually large Pauli product measurement. Many, sometimes all, of the Clifford gates in the logical circuits are compiled away. So think of your computer as implementing one big Pauli, non-Clifford Pauli rotation at one time, or PPM at one time. The other thing is that the magic state throughput is also one magic state per logical cycle. So think of it as you're producing one magic state per cycle and you're consuming one magic state per cycle. They're basically different in all other ways. Their choice of codes is different. It has an impact on space overhead. The choice of extractors is different. The choice of magic states is different. And the physical assumptions on the qubits are very different, which is why the numbers vary a lot. And the compilation resource estimation target is also quite different. There are many, many more details I won't go into. But yeah, these are some of the design choices made in recent architectures. But with this in mind, with this model of surgery architecture in mind, I want to spend the next few slides to demystify the numbers a little bit. Okay? Because for a lot of us, when we look at the announcement about the resource estimation for breaking cryptography or for factoring, it may be quite surprising or even a little bit hard to believe. So I want to spend the next 2 slides with the understanding of the surgery architecture to demystify the numbers a little bit. Now, this does not mean, I want to say the disclaimer, this does not mean that I think the numbers are achievable as they are. I think, as I mentioned earlier, there's a lot more crucial work to be done, and probably a lot of things will move. But it does mean that I think the numbers are not baseless, and that's what I want to say. So let's start with Craig's estimate as a very good baseline. As a reminder, it's surface code architecture with lattice surgery. It breaks RSA in less than 1 million qubit, less than 1 week on superconducting qubits. And it also consumes 1 CCZ per logical cycle. There's some parallelism in the implementation of the Clifford operations, but the magic is sequential. So let's look at the space overhead. I'm just going to do some back of the envelope calculation. This is not meant to be precise. Let's talk about memory. We can use high rate codes. And when I say high rate codes, I mean really, really high rate codes. They have rate 1/2, they have rate 1/3. And if you have 1,500 logical qubits, you use these very high rate codes, you can, depending on your physical assumptions, implement the memory in around 5,000 to 9,000 physical qubits. This is just the effect of LDPC codes having incredibly high rate. Now onto the compute zone. We can use smaller processor codes, or we can compute directly on memory. Because I'm doing a very back-of-the-envelope calculation, let me compute directly on memory. We're going to use single operator extractors to execute large Pauli product measurements directly on the memory. The rule of thumb that I usually follow is that it takes roughly the same size as memory to do one large PPM. It's not very precise, but it's just a rule of thumb that I follow. Now, onto the magic states, there are many designs and many parameters that can move, but we can take the standard approach. You cultivate into a surface code of reasonable distance. You load these magic states into LDPC code using an extractor, and then you distill. So there are many designs here. Depending on your physical assumptions, the number of qubits range from about 5,000 to 35,000 qubits. And this is a place where we need a lot more detailed simulation to pin down the exact cost, because this is a very important component of the computer. And you see this massive range here. It's because we don't have very thorough simulations or benchmarking to understand what it takes to output one magic state at once and to use all of these extractor gadgets. So that's somewhere that needs a lot more work. But if you put everything together, in total, you're looking at somewhere around 15,000 to 55,000 physical qubits, which is a drastic reduction from where we were just a few years ago. Now let me get on to the time overhead. So the biggest factor is obviously hardware. Neutral atom. These new estimates are done with neutral atom qubits. The code cycle in standard assumption is 1 millisecond per cycle, while on superconducting qubits, the code cycle is 1 microsecond. That is a factor of 1,000, and that immediately takes Skinny's 5-day estimates to 5,000 days. The second part that have a lot of factors is compilation. So there's the load in and load out between memory and compute. There's compilation of PPMs and of your logical control, the choice of magic states, whether you're using T or CCZ, many more factors depending on your architectural and algorithmic choices. I'm not going to go into all the details there. Another factor is logical cycle speed. So I tell you that one code cycle is, say, 1 millisecond, but I tell you that you get one magic state per logical cycle. What is a logical cycle? Well, a logical cycle is, at the moment, around 20 physical cycles, and this varies, again, based on your assumptions, but that's also a significant factor. So if you put all of these together, you see that you easily get to the order of like 10,000 days, and just by multiplying all the factors together. Yes, when I say physical cycle, I mean a code cycle, not the depths of the physical circuit. Yeah, if you look at the depths of the physical circuit, there's another factor of like 20. Yeah. Great. Now, these are just some back-of-the-envelope calculations for the numbers. I want to next comment on two things. First of all, this time overhead, obviously we don't want to run something for 10,000 days. That's a little too much. But I commented early on that time overhead in the current estimates is not fundamental, and a lot of these can be improved. So I want to go into a little more detail about that, about how time overhead can be improved. The second thing I want to comment on is the challenges that we face in building this kind of LDPC computer. Because indeed, I've shown you some back-of-the-envelope calculations. They look like a significant reduction in space overhead. But there's a lot of challenges in building that computer, and I want to highlight some of them. So yeah, time overhead is not fundamental, at least not yet. Let's look at some of the significant factors. One is magic state throughput. Right now, we are very, very sequential. We're producing one magic state at a time, and we're consuming one magic state at a time. Both of these can be improved. So we can come up with better magic state production, and we can come up with more parallel consumption for magic states with parallel extractors. Okay? So that's not fundamental, but we need to understand the cost of magic state production. Onto hardware, can reconfigurable qubits move faster? I'm not an experimentalist. We need to ask the experimental overlords. But we can implement surgery on superconducting qubits. All of the extractor architecture that I've discussed, we can implement them on superconducting qubits, which is a lot faster, but there are challenges associated with that, which I'll discuss in just a bit. The logical cycle time, I mentioned that one logical cycle is around 20 physical cycles. So can we reduce this to O of 1? Actually, I don't know why I put O of 1 there. 20 is a constant. But can we reduce this lower to maybe like a few cycles instead of 20 cycles? And the answer is yes. There are ways that you can implement surgery with constant time overhead. This is some new developments that we're just now trying to understand. And finally, in terms of compilation, I mentioned that the IBM architecture is about 10 times slower relative to a surface code architecture. And this is a consequence of the fact that their extractor is looking at 100 operators instead of 4 to the k operators. And that leads to a compilation cost of turning any gate you want to implement into the native gate sets you have. That's a factor of around 20. And this can, again, be avoided by building a bigger extractor. So all of these significant factors that contribute to the time overhead, they can be improved in future architectures. But there are a lot of challenges in building an LDPC computer, and I think it's important for us to address these challenges because we need a lot of very solid work to resolve them over the next couple of years. So one significant challenge is decoding. And I don't think this is mentioned a lot, in Siri talks, but LDPC decoding is a much harder problem than surface code decoding. This is a classical computation problem. In the worst case, it's NP complete, but obviously, normally we want to use some belief propagation algorithm. It is much harder than surface code decoding. There has been amazing progress in recent years, but we still need a lot of work to improve both the speed and the accuracy of our decoders. And just to make sure we're on the same page here, a good decoder versus a bad decoder can lead to orders of magnitudes difference in your logical performance. That can be the difference between like 10 to the 12 operations and 10 to the 9 or 10 to the 6 operations, depending on how good or bad your decoder is. Now, the second challenge that needs to be spelled out is hardware complexity. So yeah, neutral atom give us reconfigurable qubits, but even with that, implementing LDPC code in surgery won't be easy. Even though you can move everything around, we need to understand how to schedule all the moves, how to implement all the gates. This is non-trivial. And for superconducting qubits, extractor can give you universal FTQC. You can, in fact, build a full extractor for superconducting qubits. However, the connectivity needed right now for these ultra high rate codes, namely rate 1/2 or 1/3, is more than the current assumptions on superconducting qubits. So to put some numbers, some of these rate half codes, their check weight is 12. So you need degree 12 qubits. While on superconducting qubits, depending on who you talk to and how much you bug them, they are mostly comfortable, barely comfortable, let me say, with degree 6 to 8. It sounds like a small numerical difference, but for superconducting, that is a big difference, which is why this is one of the challenges we need to overcome if we want to implement these very high rate things on superconducting qubits. Maybe we find better codes, maybe we find ways to route our qubits. But those are QEC theory that needs to be developed. So, and onto QEC theory. For really large-scale FTQC beyond factoring, we need further reduction in the space-time overhead. Right now, we have pressed the space overhead a lot, and we have costed the time overhead. For larger-scale applications, we want more reductions in space-time overhead, and I think there are a lot of concrete problems here. Yes?
So just to clarify something about decoding, I thought that most of these good LDPC codes had these like greedy decoders that just do like cooling with respect to the syndrome, and that those basically work.
Yes, so asymptotically, one might say that it's kind of a solved problem. In practice, it is very far from a solved problem.
I see. So you're saying for like small code instances, those don't work so well?
Those don't work very well.
So there's the surgery system.
Also, there's the surgery system, yes.
Why these like higher quality decoders from like this, or I don't know if you're familiar with this, like there's a recent Harvard paper for computing with ultra high rate things. They just have like
yes, hierarchical decoders.
Why that doesn't just work in general? I mean,
That is a very good design. It could work. We just always want it to be better because we want it to be faster. Quantum gate speed is, we say that it's kind of slow, but it's not so slow compared to the decoding you need to do. We always want it to be better. There's a lot of progress that haven't made. Great. So yeah, onto the QEC problems. I'm going to list a couple problems that I personally found most exciting. And yeah, I think these are some good future directions for us to think about in terms of LDPC architecture. So the first one is obviously more efficient magic state factories at a reasonable cost. One way to do this is to find practical codes with low depth CCZ gates. I think we have some very good local experts here. But there's been some recent work on that. I think if this can be worked out, that would be really exciting. The other thing is we want to design the logical control together with the algorithm, because an algorithm and their subroutines, they're often quite structured, which means they're parallel. You are repeating the same subroutine many times. We want to design the logical control with knowledge of the algorithms, because that would enable us to do more parallel and more fast computation. Again, there are some works that have started exploring this direction. I think it's still very early, and I think this is very promising. Now, one question that I personally like a lot is about the practical design of these extractors. Maybe you want them to be parallel, maybe you want them to be fast, maybe you want them to be very powerful. Surgery overall is a very, very versatile technique, and I think there's a lot of opportunity for practical and finite scale studies. Even though we have already accumulated some early works on surgery, I feel like we're just starting to understand how to build things in practice. And finally, coming back to the problem of time overhead, is it fundamental? In the sense that does using these more space-efficient encoding of logical information necessarily lead to a slowdown in logical control or logical computation? I think there's some evidence that says that that might be the case, simply due to the difficulty in controlling individual qubits inside a massive block. There are some reasons that it may not be fundamental. I think this is a very nice complexity theory problem that I like to understand better. Great. So for the last few minutes, I want to end with some outlook on the early days of FTQC. Long story short, the developments in experiments and the developments in LDPC theory over the past few years have led to dramatic reduction in space overhead for FTQC. Space overhead has been one of the key bottlenecks of realizing near-term FTQC, and it's nice to see how much progress we've made. The timeline have advanced substantially. It is my belief that we'll get early FTQC soon. Now, early FTQC does not mean we'll break RSA 2048 immediately. It just means that we'll start to have logical qubits that's running logical algorithm on a non-trivial scale. The crucial bottleneck right now is time overhead. We've discussed that quite a bit. And QEC will continue to improve. So I think now is a good time for us to really talk about switching to post-quantum cryptography. Now, you don't need to believe in me, but you should believe in Craig Gidney. Here's his Blue Sky post. Is it likely that we'll break crypto by 2030? The chances may not be very high, but I think it's already at a non-trivial level that we should start acting. The other part that I would like you to take away from this talk is that extractors and low-depth unitaries, they're really analogous to classical CPU and GPUs, where the difference is sequential and complex control versus parallel and structured control. And for the next phase of FTQC, a key aspect is going to be joint optimization of the algorithm, the circuit, and the QEC implementation. And the design for FTQC systems will continue to evolve as we develop new methods, as we reach new hardware capabilities, and as we try to shoot for new algorithmic targets. And with my last slide, I want to ask our algorithm and application friends for applications beyond factoring. So once we have the first generation of FTQC, we will be looking for experiments to run on them. Hopefully that's not just breaking crypto. And this would be the perfect time to test out all of these new candidates for quantum applications that we've been studying. So as I work in QEC, and as someone who works in QEC, we'd really like to hear ideas and proposals about what we can run on these computers, because I believe that we have a great age of exploration ahead of us. And even though I'm not an experimentalist, I will go bug the experimentalist for you if you have a really good proposal. Now, there are some things to keep in mind about the proposals for early FTQC. Obviously, we'd love worst case proof of exponential time advantage, but I heard that's kind of hard, so it's not required. Large polynomial speedup sounds really good, especially, we have a lot of cortex speedups. If we can have even more than that, I think that's very promising. The goal is to discover practically or scientifically useful applications. It is okay if the performance at the near-term scale is simulable or can be approximated by classical computers. And the number of logical qubits is not as constrained now. This is one of the big things that changed over the past few years. Previously, when we think about early FTQC, we say, oh, maybe we'll have 10 logical qubits, maybe we'll have 50 logical qubits, maybe we'll be running like 10 to the 4 operations, and that'll be it. But here, now, we're talking about hundreds of logical qubits. Now, thousands of logical qubits may need to wait a little longer, but the space is not as constrained now. And I get this question a lot, which is after QEC has developed so much, from an algorithmic perspective, what is like a good benchmark for the cost or the fault tolerance cost of an algorithm, especially if you are working to reduce them? And I will say that the number of non-Clifford gates, T gates, CCZ gates, or other primitive, is still a very good benchmark. And finally, from an FTQC perspective, we really prefer circuits with more structure, such as parallel subroutines, and that's perhaps something to incorporate into algorithmic design. So that's all I have for today. Thank you.
Yeah, thanks, Sunny, for the nice talk. Are there questions? Yes.
Just a comment or a question. You spoke about applications beyond factoring. I don't think you were here at the workshop. That was 2 weeks ago when we discussed cost estimates and how to implement cryptography or cryptanalysis quantumly. But you could cut down the qubit usage to a few hundred qubits if you look at short discrete logs or discrete logarithms in Schnorr groups instead. And these are also used cryptographically, and they are quite abundant in standards and in past applications and in some current applications. There is also elliptic curve discrete logs and all, at least finite field discrete logs you could push down for, classically secure instances that would be in a few hundred qubits range, using exactly the same architecture that Craig Gidney, for example, has in mind. This would also cut the circuit down. So I think that those, if you want to look at first applications of sort of cryptanalysis, you should look at these.
Yeah, I think.
Finite field discrete log for the benchmark as a comment.
Yeah, thanks for the comment. I think that's a very good comment. That's definitely one of the things people will run on first generation FTQC.
Yeah, no, I think that would be the break point.
Can you be more quantitative when you say the magic state factor is the bottleneck?
Yes. So let me see if I have this slide. More quantitative. Let's see. So yeah. So for instance, in Craig Gidney's estimate, he has actually 6 copies of a magic state factory, but it is producing. Each factory is producing 1 magic state per 6 logical cycle, which is why he stacked 6 of them to make 1 magic state at a time. Now, if we want to get to more more magic states per logical cycle, the very natural idea is to use more copies of the factory, but that will incur space cost. Now we can think about, okay, are there ways for us to produce magic states in bulk, like what we've been studying in distillation? But one of the problem is that currently in these magic state factory design, the first step is cultivating into a surface code. Like the start of the distillation process are individual magic states coming out of surface code cultivation. And so that kind of puts a limit on how many initial magic states you can get. If you want to get more, you need to put in more surface codes. So there are, I think, people that's trying to study cultivation in a more high rate setting, just more magic states.
I guess my question is, in the diagrams that typically drawn on your slides by Oratome or by Google, the space fraction occupied by the magic state factory was not overwhelming.
Yes, that was not for, especially, okay, here's a diagram that's this is the diagram that I cut and paste from Craig's paper. This part is code storage. This part is hot zone compute. This strip of green boxes, that's the magic state factory. But now imagine that all of these, the memory, the compute, and the routing regions all got compressed down into 10,000 or 15,000 qubits. And now suddenly this is still 170K physical qubits. So once we go to LDPC code, we now understand ways to first encode with LDPC code and then compute with LDPC code that are roughly at the same rate as the memory. And now once that got compressed so much, Magic State Factory come back to become the bottleneck again. Is that okay? Yes.
Could you go back to the napkin math slide? Or I guess the slide?
There are two napkin math
Or,
slides.
sorry, yeah. Oh wait, no. Sorry, you were already on it. Well, sorry. For the like the first 3 citations for how you could get like the investments for memory.
Yeah.
Yeah. Obviously, like I should go to the paper themselves to get them. But what sort of the
Parameters with the code.
yeah.
Okay. Yeah, so these are some recent developments in QEC, really this year. They are a very high rate. And when I say high rate, I mean they are rate 1/2 or 1/3. So how did I get these numbers? You have 1,500 logical qubits. If you just do like really napkin math without looking at the codes at all, you would say, okay, 1,500 times 2, that's like 3,000 physical qubits. I need extra qubits to implement my, there are data qubits and ancilla qubits. That's usually a factor of 50% to 100%. Let me take 50%, that's 4,500 qubits. So, but to be more precise, what do some of these codes look like? So one of the codes I showed earlier on the slide has parameters 1152, 580, distance 12. Now distance 12 is not really enough for factoring, but there are larger instances of the code, and we can look at, if we want to increase the distance down to up to like 25, but still keep the block size small, how can we get there? So there are all of these trade-offs, but that should already get you that should already get the numbers on the slide.
Okay. Any more questions?
Yes.
Yeah, I was just wondering, in terms of reducing total time without reducing qubit count, are there any clean parallelization questions that are open? Or is it kind of this gigantic rat's nest of a circuit and probably want to hit it with like LLMs before you manually...
That's a great question. Thank you. I think the best way to look for parallelism is the following, is to look into your algorithm and see which subroutines show up like multiple times and which subroutines can be parallelized. And you can assume kind of, right now all the estimates are done with 1 CCZ per cycle. You can assume having like more CCZ per cycle and hope that the QEC fellows will come in and build those factories. I mean, a lot of us are trying to do that, so I feel like that's a reasonable assumption. That's a reasonable expectation that we'll get better magic state factories. So assume you have more parallel CCZ. Which part of your algorithm logical circuit can you really speed up or separate into like identical subroutines? That's going to get you like a fair amount of improvement.
I see. So it's still about parallelism in the actual algorithm rather than in the coding or other...
There are parallelism in the extra coding. So for instance, assuming, if you're asking for like QEC problems to work on, magic state factories, please. But there's also the question of consumption. You can produce all of them at once, but can you consume that many at once? And that's a problem that involves like co-design, the design of the extractor gadgets, and the routing of everything. So it's hard to give like a very clean description, but there are papers that are working on that.
How wedded are you to like preparing magic states and just the whole resource state framework as a whole?
Sorry, can you repeat the
It seems
question?
like everything you talked about was like prepare resource states and then consume them. But I think at one point you said only like half the architectures are doing this or something?
So yes, so I guess the architecture has 3 parts, right? That's actually a good question. So I did spend a lot of time talking about preparing resource states and consuming them, but the mental model I have about a modern computer that looks like this is the following. Imagine you have like an engine or fuel, right? And the logical qubits is kind of like the raw materials that you're trying to transform. And the compute unit is the whole machinery that's trying to transform the material. Magic state is the fuel for this machinery. So when I say we produce and consume the magic states, it's really saying that how can we get these like T states and CCZ states and utilize them effectively in this machinery that has been built together. So in a lot of ways, the surgery architecture is the machinery that's consuming the magic state and acting on the logical qubits. Does that answer the question?
Or sorry, but do you think this is really like the way to go? Like we want to be just producing magic states and then consuming them?
Well, there are FDQC proposals that doesn't use magic states, that uses like code switching and transversal gates. We have some local experts here, but I think they are very interesting. One of the questions I personally would like to understand better about those schemes is the scale that they're operating at. Because with these constructions, we're operating at the scale of like 10,000 or less physical qubits. But for those code switching schemes, I think, or transversal gate schemes, I think we need to understand the scale a little better. That's my opinion.
Okay, maybe one last question, if there's any. Okay, if not, let's thank Sunny again for this very nice talk. And we have a little break, and we meet again at 3:30.